Okay, where we left off in the last video was doing the different hydrogen series. So a series of lines that could be seen in the hydrogen spectrum. Now, when I say seen, I mean like seen by a computer. Obviously, we can only see the visible ones. So the first set was the Lehmann series, and that's a series of lines that falls from any higher level down to n equals 1. Okay? And they all end up in the ultraviolet range. And the series we were on, just as the last video ended, was the Balmer series. And this series of lines is when an electron falls from any higher level down to the n equals 2. This is the set that ends up in the visible range. Okay, and we had said that there were 4 lines here. From n equals 3 down to 2, that's your red line. From n equals 4 down to 2, that's your green line. From n equals 5 down to 2 is your blue. And n equals 6 down to 2 is your purple, your violet. So I say n equals 6, but like n equals 7 would also give you purple, because remember, they're going to get really close up here. And so there's not going to be a big difference. So anything above 6 is going to be in that purple line. Okay, so that's the Balmer series. The next series is when it falls from anything higher to n equals 3. And this series is called the Paschten. P-A-S-C-H-E-N. Whoops, it'd be good if I looked at where I was writing so I didn't mess it up. Paschten series. So from n equals, anything higher to n equals 3. The next one, anything higher to n equals 4. And this one is called the bracket series with 2 T's on bracket. And the last one is the Pfund. Now, you don't really say it that way, but I said it that way so you'd know there was a silent P in front. And honest to goodness, there really is. And it's from anything higher down to the n equals 5. All 3 of these series end up in the infrared range. Okay? So those are the 5 series of the hydrogen atom. By now, other atoms would have series figured out by people, but the hydrogen one is the best known, 1, because it's the simplest, and 2, because of all the work that Bohr and early scientists did on it, okay? So that's the hydrogen series. It's now time to move on to our next model of the atom. And this next model is not named after any one person, like Thomson's and Rutherford's and Bohr's were. This one is really a joint effort of a number of scientists, a number of physicists over a number of years. And I say a joint effort, but sometimes it was more of a competition or an argument. Anyway, but this next model is called the quantum mechanical model. And so we're moving into quantum mechanics. Sorry, I can't write mechanical and say mechanics at the same time. So quantum mechanics is a new theory. And earlier in this semester, you drew little names of different scientists who had things to do with this theory. The scientists here are people like, whoops, I lost an E. Told you I couldn't write one thing and say another. We're scientists like Heisenberg and Born and Pauli and Hund and Schrödinger and Heisenberg, and I don't remember who else I said, but all of those guys are contributed to the quantum mechanical view of the model. Oh, I don't think I mentioned Dirac there. And some of them were collaborators, worked together, and some of them were competitors and didn't really like each other. But our view now, this model now, is really based on all of them and all of their works. A number of them got Nobel Prizes at different times for their works. some of them probably should have and didn't. Oh, and I also didn't say Einstein in here, but he is in here too. Okay, so just first a little overview of this theory. This theory unifies the wave-particle duality, not just of light, but of particles as well. So it allows for, it shows that particles in light can act sometimes as waves and sometimes as particles. So it unifies the duality there. And so it verifies Einstein's theory of light could both be a wave and a particle, and then also de Broglie's idea that then particles could have wavelengths. It's been very successful as a theory. It has been able to explain all the things that have come up. It has looked after Bohr's limitations, and it has made future predictions. It has successfully predicted the spectra of many complex atoms. So remember where one of Bohr's issues was he couldn't explain or predict like why lines in the spectrum were closer together and why some were bright and some weren't. But the quantum mechanical view of the atom can. It can predict the brightness. It can predict where the lines are. It can explain how atoms join together to form compounds and all of that. It is, well, okay, I'm going to say this statement and then I'm going to put another qualifier in it. It is accepted today by nearly all physicists as the fundamental underlying theory of all physical processes. Okay, now there's a little asterisk that goes with that. And the little asterisk is because at speeds close to the speed of light, it kind of breaks down a bit. And that really bothered Einstein in his later years because he said, you know, it should be able to, there should be one theory that explains it all. And it's why there's been a little movement towards something called superstring. And for those of you that did term papers in Physics 12, some of you chose the superstring theory. And it's really, it's trying to see is there something beyond quantum. And for those of you who watch Big Bang Theory, both superstring and quantum are talked about in there. And there's a series of episodes where Leonard, they're older ones, where Leonard's going with Leslie somebody, I forget her last name. And Sheldon really didn't like her. But anyway, in the end, they split up because they couldn't agree on how they would raise their children. Because Leonard believed in quantum mechanics and she believed in superstring. And it was like, that was the tipping point for them. It was like, okay, like we can't have them confused. So anyway, so there is, like, this isn't done. You are going to hear me say in this unit oftentimes, we believe. We believe. Physics isn't finished. We're pretty good on the kinematics and the sum of the forces in our concrete world, but as soon as we get to minuscule, when we get onto that subatomic level, there is such a truckload of stuff that we still don't know. And the same is true when we go into the huge level into outer space. There's a truckload of stuff we don't know. All right, so the first thing in the quantum mechanical theory of the atom that we need to look at is something that is called the wave function. Okay, now it has its own special symbol. It's a Greek letter. It's the Greek psi. Kind of looks like a pitchfork if you're a farm girl or boy. It's a capital, and psi is spelled P-S-I. Okay, and it stands for the wave function. Now, to explain what the wave function is, you have to think about, when we talk about any wave, there are three properties that are important. Those properties are the wavelength, the frequency, and the amplitude of the wave. So how long the wave is, how many frequency and amplitude, amplitude. So how long the wave is, how many waves per second, and how much energy, or what is the magnitude or the amplitude of the wave. Okay, so think about water waves. We know all these, even light waves. Now we